And this will be given by Frederic Bouly. And the title of this presentation is Euratom Max Program, the MYRRHA Accelerator Experiment. So it's about the MYRRHA project. Please, Frederic.
Okay, thank you. So I come back now on LINAC accelerators for ADS. And my talk is about the Euratom Max project, which is focused on R&D activities for the MYRRHA ADS. So my outline is the following. I will just describe first the accelerator concept for MYRRHA now, which is, LINAC, superconducting LINAC for protons. And I will show you the recent achievements in R&D activities and what's going on. And then I will conclude with some perspectives. And first of all, as an introduction, then I recall you that MYRRHA means multipurpose hybrid research reactor for high-tech applications at MOL, to be built at MOL in Belgium. It aims at the development, the construction of, and the commissioning of a new large fast neutron research infrastructure. It will be first facility to demonstrate the ADS technology, but it also can be, as it was explained by Amit on Monday, a fast neutron irradiation facility, and it also can be a pilot plant for lead fast reactor technologies. And so my introduction is, I would like to give you some backgrounds on the history of the choice of a LINAC for MYRRHA. So, as was already discussed before in the previous talks, the R&D activities on the ADS accelerator started during the 90s through several projects, like, for example, ThEC13 in Europe. And in the European Technical Working Group on ADS, gave a first roadmap in 2001 for a design of ADS with a cyclotron. At the same time, in 2002, the pre-design of MYRRHA was also with a cyclotron of 350 MeV. From 2002 to 2004, MYRRHA was studied as one of the 3 reactor designs within the PDS XADS FP5 projects in Europe. And the first reliability analysis introduced the fault tolerance concept. And in this way, the cyclotron design turned into a LINAC. In 2005, MYRRHA also updated its design of accelerator into a LINAC of 350 MeV. And then from the next project was the Euratom's project in the LPSL in Europe. And MYRRHA was studied at the demonstrator facility, and the energy of the LINAC was then frozen to 600 MeV. And nowadays, within the MAX project, we are continuing the R&D activities for the MYRRHA accelerators. And this is an ongoing project. And we are continuing the research and development activities in view of a possible construction phase for the next following years, and the possible commissioning of the machine after 2020. So MYRRHA within the Euratom FP7 program, it revolves around different projects. So the central design team, which was focusing on the reactor design. FREYA is a project which is supporting the experimental activities around on ADS, and in particular the Grenoble experiment, which is a low-power ADS facility at ThEC13 in Belgium, and MAX is the projects for studying the accelerator of MYRRHA. So the goal of the MAX project is to deliver a consolidated reference layout of the MYRRHA LINAC with sufficient details and adequate level of confidence in order to initiate an advanced engineering design and a subsequent construction phase. It involves many different partners. It's coordinated by CNRS in France, and it of course involves ThEC13 and also different universities in Frankfurt and different companies like Empresarios Agrupados, ADEX, or Thales for the developments of cryogenic power plants, control systems, and RF power supplies. And I come to my second part, so the MYRRHA accelerator concepts. So just a short reminder of what MYRRHA is. It's a reactor which can be operated in a subcritical mode, which will produce between 50 and 100 thermal megawatts. The fuel for the moment is supposed to be highly enriched MOX, and the target for the to produce the spallation neutron will be a lead bismuth aseptic, and this spallation neutron will be produced thanks to a linear proton accelerator, and the specification for this accelerator is to produce a beam of 600 MeV with a maximum current of 4 milliamps. So it's already a quite high power accelerator, which can, so the maximum power could be 2.5 megawatt, 2.4 megawatt. And okay, this was already shown by Alex before, but if you have a look to the panorama of high power proton accelerators, so here you have the mean beam current on target for different accelerator, and here it's the beam energy. So as a reminder, PSI is here and MYRRHA is way just above. And just to comment again what was already said by Alex, is that we can see that MYRRHA is already in the group of high power proton accelerator, but still it's on the basis of the state of the art. Now it's on the same basis that SNS or the European Spallation Source project. And the real challenge for the accelerator of MYRRHA is really the reliability. The requirement for the moment is to have less than 10 beam trips, longer than 3 seconds per operation period. So where does it come from, this 3 beam trips? First of all, you need to limit the thermal stress and the fatigue on the different elements of the reactor, of the target, and so on. And you also need to ensure at least 80% availability of the ADS facility. And given the forcing reactor startup procedures, you cannot really afford to have a beam trip per day longer than 3 seconds. Otherwise, you need 1 day to restart your reactor, and then you never use your ADS. So the present specification, as I said, is 10 beam trips. You must, during a 3-month operation period, you must keep the number of beam trips longer than 3 seconds below the number of 10. The specification is derived from the Phoenix reactor operation analysis, and it's of course far above present high power proton accelerator performances. So I show also this thing again, where you see the number of beam trips per day as function of the trips durations. For example, if you compare MYRRHA, which is the green curve, to the SNS, at SNS in Oak Ridge, then you see that you have 2 or 3 decades to win in terms of reliability. So in any case, we need a reliable guidelines and a reliable accelerator. So we need a strong design for this accelerator with robust optics. Try to keep the accelerator as simple as possible. And we have to design the accelerators by keeping with operation margins. If we can produce a beam of 4, if we want to produce a beam of 4 milliamps, we must be able to produce twice as much or 3 times as much. Of course, in designing the accelerator, we have to also make it easily repairable with online repairability if possible. And redundancy is also an important point. If you want to be able to tolerate failure, you must favorize redundancy in your installation. So redundancy in the MYRRHA LINAC, so how it works, what is the strategy? So first of all, for the injector, the idea is that as in the injector, every element is unique. You cannot use one element in the injector to compensate the failure of the other one. So the idea is to make a compact injector and to have 2 injectors. And if you detect a failure in the first injector, then you have a spare one, and you have to switch from one injector to another in less than 3 seconds. In the main acceleration line, so in the main LINAC, which is superconducting, serial redundancy is possible. You have several times the same cavity, and the idea is here that if you have a failure, you detect this failure, Once it's localized, you retune the adjacent cavities. So for example, if you have one failed cavity, you retune two cavity upstream this failed cavity and the two cavity downstream, and in this way you restart your beam, and the goal is to do it in less than 3 seconds. So a total view of the accelerator. This was already shown by Amit on Monday. So you have the main injector building with the 2 injectors, and then the beam goes in the main acceleration line, which is composed of the first family of spoke cavity, 2 cavities per cryomodule, then a second family of elliptical cavity with 2 cavities per cryomodule, and the last part is composed of also of elliptical cavities with 4 cavities per cryomodule, and here it's the line for injection in the reactor. And you have a view of what the building could look like at ThEC. So some recent achievements in R&D for the MYRRHA LINAC. So what I will try to do is to go step by step through the LINAC, starting from the source to the end of the acceleration line, and telling you what is going on the R&D side. So first of all, the source and the low energy beam transport line. So the LBT conceptual design is achieved, and we are not even in the detailed technical design, but in the construction phase of this beam line. The source is already at ThEC for commissioning, and all the line will be manufactured and installed at LPSL in Grenoble, and we will do a complete test of this line at LPSL in Grenoble. This will also be the opportunity to do nice beam physics on this small beam line, where we will study the space charge compensation effect with the residual beam gas. So you keep some residual beam gas into the line, and in this way you can compensate the space charge of the beam by ionizing this gas. The electron so you create pairs of ions and electrons. The ions are ejected by your proton beam, and the electrons are kept by the proton beam in such a way, and they create a screening effect between your protons, and then you can compensate the space charge effect. And this beamline will be, in terms of magnetic elements, there will be no electrostatic focusing, but only 2 solenoids for the focusing. Then the beam goes into the RFQ for the bunching of the beam. And the present reference design for the RFQ is a 4-rod structure operating at 176.1 megahertz. The R&D's activity are done at the University of Frankfurt, and the main topic was to find out how we can have a thermal cooling, an efficient thermal cooling of this RFQ. And now a prototype was constructed, a 1 meter long prototype, and it's going to be tested in next months. And of course, the next step will be to build the 4 meter long RFQ for the injection line. This can be taken by ThEC. After the RFQ comes a booster with CHDTL cavities, room temperature cavities, and superconducting cavities. And the idea was to use superconducting cavities as CHDTL to make the booster as compact as possible. And for the moment, well, it's also developed at the University of Frankfurt, and they have a prototype of superconducting cavity CHDTL, which will be tested soon as well, and also a prototype of room temperature CHDTL cavities. A couple of words on the medium energy beam transport line. So a conceptual design exists, so on how you transport the beam from the injectors to the main acceleration line. There's also beam dumps foreseen here for the commissioning, and one has to be studied in more details the switching magnet procedures to switch from one injector to the other one. Regarding the main superconducting LINAC, so there's a reference design which is composed, as I already mentioned, of a family of superconducting spoke cavities, a family of 500 cell elliptical cavity, and another family of 500 cell superconducting elliptical cavity. Regarding the spoke cavity, there's a design, consolidated design, full mechanical design, which was achieved at IPN Orsay, and the prototyping of 2 MYRRHA spoke cavities was launched, and are expected to be at Orsay next year. Regarding the 5 cells elliptical cavity, there's already an experiment existing at Orsay with a prototype of cryomodule with 1 accelerating cavities. The cavity has already been tested and gave very good results in terms of performances. Here, okay, I should make it bigger. But here you have the quality factor of the cavity versus the accelerating field. The MYRRHA working point is here, and the blue curves give you the maximum performances of the cavity. And now we condition the power couplers, and everything will be installed for real scale tests. And the goal of this experiment will be to be a test bench for reliability or oriented activities to test how we can retune the cavity and how fast we can do it. We have a baseline for that, and we have a goal we want to reach. Basically, we want to be able to demonstrate that we can do this retuning in 100 milliseconds. So the RF retuning is not really an issue, but the thing is to show that we can retune the frequency of the cavity by applying mechanical deformation on it in less than 100 milliseconds, and to do it very accurately. So to study this, we developed some models of the cavity, and on the feedback system, this model enabled to understand what kind of feedback system we will use, and we are developing it. And at the same time, also the simulation and thus retuning the new set points of the cavity were determined by beam dynamics simulations. And these beam dynamics simulation also enabled to dimension how much RF spare power we need for the amplifiers, which is around 60 or 70% margins compared to the normal operation of the LINAC. All these beam dynamics simulations are based on the reference design, which is now consolidated through the MAX projects. So this reference design is really a start to end design from the source to the target. There were also some benchmarking activities, so the design was benchmarked between different codes like Traswin, Lorasar, and ThEC, and the Monte Carlo error study are performed. Another important point on beam simulations during MAX is that the time structure of the beam was also defined by working with people on the reactor side. And here you can see that actually the beam will not be completely CW, but you need trips to monitor the subcriticity of the reactor. So what it will be for MYRRHA is that you will have the beam very long pulse of 4 milliseconds. So you will have the blue pulse will be what you send to the reactor, and you need a 200 microsecond hole to monitor the subcriticity. And a possible idea which is coming is that you can use the part of the beam that you don't send to the reactor to another facility, like for example a kind of ISOL facility, which could be ISOL at MYRRHA facility. And finally, regarding the high energy beam transport line, so there's a preliminary design which exists, but the interface with the reactor has to be further reworked, and the interface with the window in particular. Another important R&D activities is the activities carried out by Empresarios Agrupados, which is building a reliability model of the accelerator of MYRRHA. So what they did first is that they built a reliability model of the SNS LINAC, and they successfully benchmarked this model with the operation data from the people of SNS. And now, from this model, they are transforming it to the LINAC of MYRRHA to make a strong reliability analysis and to find what could be some weak points and how we can improve it. And we are also having some R&D activities, especially on RF amplifiers and on the development of solid-state amplifiers at 700 MHz to make these elements, which are quite fragile in the accelerator, more reliable. And then I come to my conclusion. So the successful and reliable production of the MYRRHA high proton, high power and stable MIMI is a very interesting challenge, especially in terms of reliability. But R&D investments are still needed, and presently we are really investing in those R&D activities through the construction of the injector of MYRRHA. It has started with the low energy beam transport line, which will be installed and tested in Grenoble. And there are several prototyping activities on CHDTL activity, RFQ, and there's one experiment running at Orsay on superconducting activity to study these fault recovery capabilities of the LINAC, and there will be some spoke cavity manufacturers as well. And MAX is still going on until October 2014. And a possible follow-up is under study for the next years. And of course, if the project is built, there will be a need to have a strong accelerator team at ThEC13 in MYRRHA. I thank you for your attention.
So thank you very much for this presentation, which was loaded with a lot of facts. And thank you also for staying in time, so we have time for some questions, please.
Thank you for your very good presentation. I have one question. You are using the spokes type RF cavity for the design and manufacturing? Spoke type.
Yes, we are
RF cavity.
We are using single spoke cavity. Yeah.
It's a very high voltage. So that do you have any solution for against the multifactoring problems?
Yeah. So the multipacting problem has to be studied. So in Orsay, there's a development on codes to simulate the multipacting and understand what is happening. It has been benchmarked on several cavities now and benchmarked with the experiment. And it is also shown that if you adapt the design of the spoke cavities now, then you can get rid of some multipacting. This is one solution. The other solution is that if some multipacting also appears on the LINAC, then the idea is that you switch off this cavity and you have sufficient margin to compensate this cavity that you do not use with the other ones.
Other questions? I see one over there.
Are there any cost comparison between cyclotrons and LINACs?
To my knowledge, no. Maybe Alex knows better.
It depends, of course, how much fault tolerance and so on you put in. It also is very strongly dependent. You see, the cyclotron is very, very heavy, needs a very large hall, whereas the LINAC needs something which is only 3 meters wide, but very, very long. So that has then incidence. You have to see the local construction site. But in first order, a fully reliable LINAC, to what I see, is about 25% more expensive than a cost-optimized cyclotron. So it's not factors of 2, 3, or something like that.
Okay, I think
I speak for the same intensity, of course, and I speak of several. I'm not speaking of a 300 MeV, 1 milliamp cyclotron compared to a 30 MeV.
So, excuse me, Alex, but with this kind of figure, 25%, I could not agree with that. You saw the design I was presenting is much less expensive. Probably. If we would speak about price, that will take some time, but it would be interesting to have a detailed discussion about that.
Okay, other questions to this presentation? There is another question over there.
Some question. Which efficiency you intend to have electrically? Electrically, how much you intend to put to get your 2.5 megawatt, how much electricity power you need?
But you have to take the convention factor of electricity and hive power system itself, and in first approximation, if you consider that you have more than 90% efficiency for the superconducting cavities, then it's like 35% efficiency.
Yeah. But you need to include the cryogenic plant, of course, right?
And
Hamid wants to answer this.
Yeah, if I can try to give not a technical answer, but the one who will be paying the electricity answer. So in our business plan, as I said before yesterday, we are taking that the efficiency that we will be getting for our accelerator in terms of electricity is 10%. But I am pushing those guys to get me better than that. But in my business plan for the operation of the machine is 10%. So which is, I am happy to hear that we are not far away. But if those guys can get me 30%, 50%, I will be a happy man.
Okay, then I think we can move on. Let's thank the speaker again.